Welcome to the video on electric charges and fields, Chapter 01 of Class 12 Physics. This is an introduction to static electricity and fundamental forces.
Let's start with the foundations of electrostatics. The spark experience, the crackle when taking off clothes, is caused by the discharge of accumulated electric charges. This phenomenon, known as static electricity, is generated by rubbing insulating surfaces. What is electrostatics? It is the science of static, dealing with things that do not move. Electrostatics studies forces arising from static charges, electric fields, and electric potentials. Historically, in 600 BC, Thales of Miletus observed that amber rubbed with wool attracts light objects. The Greek word for amber, electron, gave us the word electricity. Early experiments showed that rubbing pairs of materials results in an ability to attract light objects. Through rod experiments, we observe that like charges repel each other, while a glass rod attracts a plastic rod. This leads to the conclusion that there are only two kinds of electrification, differentiated by the polarity of charge. Benjamin Franklin named the two kinds of charges, positive and negative. He noted that unlike charges neutralize each other's effect. By convention, glass rods and cat's fur are positive, while plastic rods and silk are negative. The gold leaf electroscope is a simple apparatus used to detect and measure charge. It consists of a metal rod and two thin gold leaves. Touching the knob with a charged object causes the leaves to diverge, and the degree of divergence indicates the amount of charge. Conductors readily allow the passage of electricity, having free electrons that move easily, like metals or the human body. Insulators offer high resistance, and charges stay localized at the point of contact. Examples include glass and plastic. Now, we will explore the basic properties of electric charge: additivity, conservation, and quantization. Charge is a scalar quantity. The total charge for a system is the algebraic sum of all individual charges. Q equals Q1 plus Q2, and so on up to Qn. Remember, proper signs must be used during addition. In an isolated system, charge is conserved. Total charge always remains constant. Charges are neither created nor destroyed, only redistributed. For example, in beta decay, the net charge remains zero before and after the process. The quantization of charge states that all free charges are integral multiples of a basic unit of charge, E. This is represented by Q equals NE. The value of E, the fundamental unit of charge, is approximately 1.602 by 10 to the power of negative 19 coulombs. Next, we will discuss Coulomb's law, the fundamental force law governing electrostatic interactions. The force between two-point charges, F, is inversely proportional to the square of the distance, R. It is also directly proportional to the product of the magnitudes of the charges. This relationship is expressed as F equals K times the absolute value of Q1 times Q2 divided by R squared. For convenience, the constant K is expressed as 1 over 4 pi epsilon naught. Epsilon naught is the permittivity of free space, with a value of approximately 8.854 times 10 to the power of negative 12 c squared n inverse m inverse 2. Coulomb's law can be expressed in vector notation to include direction. The force F21, acting on charge 2 due to charge 1, is calculated using the formula shown. This law inherently obeys Newton's third law, meaning F12 equals negative F21. The superposition principle states that the total force on any charge is the vector sum of all individual forces exerted by other charges. This means individual forces are unaffected by the presence of other charges. We move on to section 1.7, electric field. This concept allows us to characterize the electrical environment created by charges. The electric field E at a point R is defined as the force experienced by a unit positive test charge. Its SI unit is Newton per Coulomb. The force on a charge Q in this field is given by F equals QE. Visualizing field lines provides a pictorial map of the electric field. The density of these lines shows the field's strength, and the tangent at any point gives the net field's direction. For a point charge, the lines are radially symmetric. Key properties of electric field lines include starting at positive charges and ending at negative ones. In charge-free regions, they are continuous curves. Importantly, they never cross and do not form closed loops. Next, we explore electric flux, which is our way of measuring the electric field passing through surfaces. Electric flux measures the, quote, flow of electric field lines through a surface. It is calculated using the dot product of the electric field and the area vector. The area vector is directed normal to the surface, and the unit of flux is Newton-Coulomb inverse meter squared. Section 1.10 introduces the electric dipole, a pair of equal and opposite charges. An electric dipole consists of charges positive q and negative q, separated by a distance 2a. The dipole moment vector, p, is calculated as q times 2a. Its direction points from the negative to the positive charge. The electric field on the axial line of a dipole at distance r from the center is given by the formula shown. For large distances, where r is much greater than a, the simplified approximation is also provided. For a point on the equatorial line, the electric field is also given by a formula. Again, for distances where r is much greater than a, the field simplifies, showing a dependence on r cubed. When a dipole is placed in a uniform electric field E, it experiences a torque given by the cross product of P and E. The magnitude of this torque is PE sine theta, which tends to align the dipole with the field. Finally, we discuss Gauss's law, a powerful tool for analyzing situations with symmetry. Gauss's law states that the total electric flux through any closed surface is proportional to the net charge enclosed. This law holds true regardless of the shape or size of the closed surface. We now apply Gauss's law to find the field of an infinitely long, straight, uniformly charged wire with linear charge density lambda. The resulting electric field is radial and independent of position along the wire, as shown in the formula. Next, we examine the field of an infinite plane sheet with uniform surface charge density sigma. The electric field is uniform and independent of the distance from the sheet, given by the expression E equals sigma divided by 2 epsilon naught. For a thin spherical shell, the electric field depends on whether the point is outside or inside the shell. Outside, it acts like a point charge at the center. Inside, the electric field is 0 because no charge is enclosed. This table summarizes the different field dependencies we've covered, from the inverse square law for point charges to the specific dependencies for line, plane, and spherical shell charge distributions. Thank you for exploring electric charges and fields in this video. Keep inquisitive, stay grounded.